We're good? Okay, so this presentation is about pwning. It's binary exploitation. And what binary exploitation is about is just taking any kind of compiled program and putting some kind of user input that was not expected by the developer. And what this user input does is it makes the binary execute certain code that was not meant to be executed. It could even be code that was not even part of the binary at all when it was compiled. And I'll be giving demos on arbitrary code execution. That just means that I put any kind of code in the binary through assembly. And the first thing about binary exploitation is that you got to be mean. And by being mean, I mean you do exactly what the programmer didn't intend you to do. And what that means is, for example, there could be a buffer of, let's say, 200 bytes. And what the programmer expected you to do is put in a kind of user input that's 200 or less. Of course, there are mitigations, but that's for later in the presentation. But what they could be using is stuff like the get function or the string copy function. And the thing about the string copy function is that we will be it's not talked about as often as the gets function, but it's still nevertheless important to go over. And another thing is that you got to be thinking outside the box. You got to be looking at certain code, whether it could be a gets, it could be printf. That's another seemingly harmless function that could be exploited if it's programmed incorrectly. And another thing about binary exploitation is it's not just trying like huge length. It could be about putting certain characters in as well. That's more common for the higher level kind of programming languages, not C. C is more one of the low level programs. So I'll also be looking at Python in this presentation, which was written by another member of this club, of the computer security group, Henry. And the number one thing you got to think about when you try to exploit a binary is think, where does the program ask for user input? Because only in those areas in code and in any place in cybersecurity in general, vulnerabilities come from user input. So that's where you got to be focusing. About the user input, you got to be thinking, as when you are developing code, you got to be thinking not just from your point of view, you also have to be thinking from the attacker's point of view. Because as a developer, you want to create the most secure programs possible so that your company doesn't end up spending $1 million, $2 million, or even more from some kind of breach because your code was insecure. And a big part about making your code secure is separating your data from user input. And this is not only true in compiled binaries, it's true for SQL injections as well, and SQL injections could be very critical vulnerabilities. So you should never, ever trust user input. Doesn't matter who it's coming from. And you should never use dangerous functions. So in this, now I'll be showing you a demo on what I mean by this. So we'll start with Python because it's the easiest to understand when it comes to binary exploitation. It's just thinking outside the box. So we have this program called bank.py. And what it does is it just asks you, would you like to withdraw money? You have $1,000 and you can withdraw money. So let's say we want to withdraw and we want to withdraw $500. So we withdrew $500 and now we're left with $500. So as an attacker, you got to try all kinds of different things. What if you withdraw $1,000? Would you be left with negative 500? No, it says you do not have enough money to withdraw. All right, so let's withdraw another 500 and see what happens. So now we're at $0. And we could just keep on withdrawing more and more and more, but we can't do anything at this point. So another thing as an attacker is you're usually not given the source code, But for sake of understanding and learning, we have the source code and we will be analyzing it. So we are first given 1,000. This is our $1,000. And then a series of print statements are that they come after this amount variable. After that, it asks if you would like to withdraw. And it just says if this equals if you do want to withdraw, then it asks you how much. And after you put an input, if you put some kind of amount, it says the amount that you have, which is initially $1,000, gets subtracted by the value that you put. This is why when I put 500, I was left with an amount of 500 because 1,000 minus 500 is 500. But something's very interesting here. Amount minus equals is just the same thing as saying amount equals amount minus value. And when we put 500, this math equation said amount equals 1,000 minus 500. Well, what number subtracted by another number will give you a number that's even greater than the original amount? Well, this is exactly the kind of mindset that you have to have when you're trying to exploit binaries, because after thinking a while about that, you'll realize that if you put a negative number, let's say 4,000, you got negative $4,000 withdrawn, and we have $5,000, which is more than the 1,000 that we started out with. So now you can be super rich. You give yourself all this money, and you became more than just a millionaire. You became whatever that is. Probably my little brother would know how to say this number. But anyways, that is the idea of that program. It's a very simple program just to teach you thinking in the mindset of an attacker. The next program is secret.py. And just like last program, I will not look at the source code first. First, I'm going to be executing this. So it says, give me a number. Okay, let's give it a number of 5. Another number. All right, let's give it 3. So we get number 1 plus number 2 equals 8. And this, the fact that it printed this out is already very interesting, because this might seem like it's some kind of just like a capture the flag kind of challenge, some kind of CTF, but these kind of tests are prevalent even with like stuff like server-side template injection, where you're going to be trying to adding 2 numbers. You do something like 7 plus 7 and see what the server responds with. Does it respond with 14? Does it respond with 7, 7? Does it respond with 7, 7, 7, 7, 7, 7, 7 sevens, basically? What does it do? And that is that kind of evaluation function is something that we have to be thinking of. It's always got to be at the back of our minds. We could put some other numbers. Let's see if we just put random garbage. Just some, and this traceback, the fact that it said P, whatever this long string that I wrote, it says it's not defined, which means it's performing some kind of evaluation on this particular string. The program thinks that this string is a variable. And that is a huge vulnerability, because we can see even from this traceback that it's printing some kind of evaluation on number 1, which is what we put right here, and number 2, which is what we put here. And this evaluation function is extremely dangerous, and it should never be used. That, and also there's many functions. Python also has a system function where you need to import the OS module, and what that does is just run system commands. So the fact that it's running an evaluation function means that what we could do is perform some kind of Python programming line. Like we could write some kind of one-liner. We could write a reverse shell, for example, or we could just do something simple like print this is insecure. Print yes. And yes, it does have a traceback arrow, but that doesn't matter, because the program executed this print statement. It executed print, this is insecure, and I know that because it printed it right here, and it also printed yes. It didn't print the actual string print parentheses that. It actually printed it actually evaluated that print statement. So the goal of this challenge is to leak a password that is present in the program. So you could, in an actual engagement, you could like brute force a whole bunch of different names if you felt like it. You'd probably just get a reverse shell, really. But we want to leak I'm a secret. Okay, well, it's not that much of a secret because we can see the source code. But anyways, let's execute this. So you can print any kind of variable in a program, in Python, by just writing it like this without the quotations. And let's just put some random thing. So we printed out this secret, XXX top secret password, and the binary was exploited. And this was all because of the evaluation function, which should never be used. So that was just an introduction to thinking like an attacker. So now let's go a little bit more advanced and go over a buffer overflow example. Now a buffer overflow occurs when the user's input exceeds the amount of memory allocated to a certain buffer. So let's say we, as a developer, we say, okay, this buffer, let's allocate 500 bytes to this buffer. And then let's ask the user to put in his name, maybe his first name, his last name. So we say, what's your first name? And we're expecting a name like, I don't know, Mark, Rick, 4 letters. People don't really have names that are more than 100 letters long. So we're not nice. I think, again, we're being mean. So what we try to do is we just say our name is A 500 times. You know, we'll flood it. We'll put it 600 A's, whatever. Doesn't matter. But what we're trying to do here is just try to overflow the buffer. The buffer's expecting just a couple characters, and we just spam it with a whole bunch of letters. And the reason why I put this image of a cup with water leaking out of it is because this is very symbolic of how a buffer overflow really is. And to really highlight this, we can go on plays.org. It is a game for kids. And here, plays.org/happy-glass. Hopefully my internet's not too bad. So what we're doing is, this is what the developer expects. He expects, 4 letters. We give the cup just this amount. It's fine. It's not leaking. Everything's good. But as an attacker, we're mean. So we just keep on going. And we don't stop. And this is just all of our bytes just flooding into the cup. And eventually the buffer can't take it anymore, and it just floods. And it just leaks onto the table. And the table is the other memory spaces of the program. Now, that was kind of a childish example, but let's actually really do this for real. Okay, so here's what the program looks like. Very simple, just 16 lines of code. We have a main function, as is very common in C. You have a main function. Then you have a buffer of 128 bytes. After initializing this buffer, we ask for an argument. So an argument to the program. So then with the argument, let's say if this argument did not exist, then we say, okay, you got to put an argument. All right, so let's say we put in an argument. Then what it does is use the string copy function. Now, the reason I'm giving this example in particular, not like gets, is because gets is very popular. Everybody shows gets, but string copy is not talked about as often. And there's something very important about this because if you look at the man page for gets, it explicitly says never use this function for gets because it cannot tell, it doesn't perform any kind of boundary check, and it's easy to overflow the buffer. But it doesn't say anything about never use this function for string copy. But it's kind of hidden, and it's in the bug section. And it says that it could be exploited. Where is that? Mentioned at the top. Beware of buffer overflows. Buffer overruns. It says beware, but it does not say never use this function. And I think that string copy could really be overlooked as a potentially vulnerable function. So after, oh, sorry, you have a question?
You can't make the screen a little bigger.
This screen?
The text is kind of tiny.
Oh, sorry about that. Let's see. Preferences.
I think if you do Control plus, it should. Okay, no, it doesn't.
Profile preferences.
Control Shift plus. Sorry,
Control Shift plus. Oh, yep. I guess Control Shift minus is nope. Control Shift minus
no,
is
it's like because it's Shift plus is plus. Just press equals plus equals. Yeah, this equal.
Uh-huh.
Yeah, if you just do Control minus, then it's just.
Okay. All right, so after putting in an argument, it just prints out that argument. That's all this program does, basically. So let's execute it. As expected, it says you want to add an argument, so let's put 5. I don't know, it just prints out 5, the string 5. All right, but remember, we're really mean, so we don't put just the number 5. We put, I don't know, what was the buffer again? It said 128 bytes, that's right. Let's put, just to be mean, let's put 500 A's. Segmentation fault. And when you see that a program has a segmentation fault, that is a huge red flag, because that tells you that you were able to crash the program by putting tons of like a huge length of user input. That could be a result of a buffer overflow, and we will verify that by using GDB. And all GDB is just a debugger program. All it does is it really shows you each step of the program in assembly, which is a really low-level language for programs. So let's put what I'm going to do is cyclic right here. And actually, before I do that, I'm gonna just do this A again to show you that the return pointer gets overwritten to 41414141. Now this is this number, this hexadecimal value 0x41 corresponds to the capital letter A. Where is it? /41. Here. There it is. A corresponds to the hexadecimal value of 41, which is 65 in decimal. So all of these 41s here are really just our A's overflowing into the EIP. The EIP just stands for the instruction pointer. And this is for a 32-bit binary, which is why it's EIP and not RIP. So with that, let's we have the source code, but as an attacker, we tend to not have source codes. So we're just going to put a cyclic function. Well, all the cyclic is just this certain command that puts a certain pattern of strings. It looks kind of like this. Just AAA, BA, and the reason this kind of string in particular is a special string because it's meant for showing you the offset. It's meant for showing you how many bytes you need to put in before you overwrite the EIP, the instruction pointer. Or it could be anything. It doesn't have to be IP. It could be EBP. It could be some part in memory that's not really associated to like the instruction pointer or anything. So as we can see, we have an invalid address at this 6261. So we could do cyclic-L followed by this. And what we see is that we have to input 132 bytes of data before the instruction pointer gets overwritten. So just to verify that, what we could do is run the program again. This time we give it 132 A's, and we give it 4 B's, just like this. And 4 B's in hexadecimal is, or just 1 B is 42. So if we have 4 B's, that would be 42, 42, 42, 42, 42. So we're expecting now the instruction pointer to be 42, 42, 42, 42. Oh, looks like I forgot to put a print right here. And as expected, the instruction pointer was successfully controlled because we predicted that it would be 42, 42, 42, and it is. So the next part about binary exploitation, now that we have the instruction pointer completely controlled, we can go to any point in the binary, any point at all in the binary that we want, any point. But most importantly is that we can now pass some kind of arbitrary code into the program, and as long as there's executable sections in the binary, we can execute that. And so it's important to run the checksec function on the binary before we verify this, because the checksec function will tell us exactly if this is possible or not. And as we can see, NX, the bit that's responsible for the validity of shell codes or not, is disabled. And because it's disabled, it means that we can put shell code within the buffer and then point the instruction pointer to that shell code, and that shell code will be executed as if the programmer put like some kind of system bin sh into the program to give you a shell. There's some other kinds of security that is disabled for this binary, and I'll be talking about this kind of security later in this presentation. So we have successfully controlled the instruction pointer. So the next step is to put some kind of shell code in it. And you could just go online right here. You just type in bin sh shell code. There's like a 23 byte shell code, 22 bytes. I already have that on my system, so I'm just going to take that. It's this is the 22 byte bin sh shell code, and it looks something like this, which looks kind of strange because it's just a bunch of hexadecimal values. But what it really is these hexadecimal values, they represent certain opcodes and certain operations for the program to execute. This is assembly. And when you put this as user input into the program, remember that the computer really just executes machine code at the very, very lowest level. And before the machine code, you have the assembly. So it doesn't matter that the program is in C. That doesn't mean that you can't put assembly in it, because assembly is the lowest language other than machine code. Okay, so we copy this, 22 bytes. Remember that we have to fill up 132 bytes before we put in these 4 B's. So that's why I subtracted 20 from 132, which is 112, so that I could put in, actually, a best practice is to do something like this. We give 102 A's, followed by the shell code, which is 22 bytes. So now we're at 122 bytes before these 4 B's. And now a very key part to this binary exploitation in general, when it comes to compiled binaries, is NOP sleds. So what a NOP sled is just 90 in hexadecimal, which refers to NOP, no operation. It's assembly code that tells the program to do absolutely nothing. It does absolutely nothing. So you would think, how could doing nothing be useful to an attacker? Well, it's useful because when we put our shellcode into the buffer and surround it by a whole bunch of do nothing do nothing opcodes, then we can point the instruction pointer to anywhere within that NOP sled, and the shellcode will execute as expected. It just gives, it's not exactly necessary, it's not 100% necessary, but it just gives like a bigger cushion to where you can put your instruction pointer. So with that being said, this is 90, the NOP code, or NOP opcode, and we're going to give 10 of those because 102, you see this A times 102, plus the shellcode, plus 10 NOP sleds is equal to 132. But let's change this A to the NOP sled as well. So now, I think I might have 112. Oh, yeah, you're right. It's 134. My brain is fried from a different math class, so. Okay, this is probably fine. Let's see, where's the EIP? EIP now points to some strange value, 73.2F2's F6E, because we didn't exactly, this B is 42, 42, 42, and maybe that went to some place in memory that then got translated to the shellcode. A whole bunch of complicated stuff. It really doesn't matter that much. What really matters is now looking at the buffer here. So when we look at the buffer, we are let's show here like this. Okay, so here's a whole bunch of places in memory. We got FFF, all these random places. It leads to somewhere in memory in the binary that's useful. But what we're really looking for is these 90s here, because this is where our input starts. All those 90s are right here. And this is, if I remember correct, is it 100? Yeah, 190s. And after this 190s, we have our shellcode, which starts right here at 0xffced8 plus 4. And the reason it's plus 4 is because this is 4 bytes. 1, 2, 3, 4. So we just do this hexadecimal plus 4. And now we are right here. This is CEDC. So this is important to know because when it comes to this instruction pointer, that means we want to do any kind of instruction. We want to point this to anywhere between CE78 and CEDC. So this is the benefit of putting NOP sleds, because you can just point it to here, for example. And remember, you're going to want to put this in hexadecimal because just to be consistent with all of this, it's important that you put hexadecimal. Another very important thing to understand is that this binary is in little endian, least significant bit, which is little endian. And what the reason that's important to note is because when we input our string, our malicious string into this binary, we want to start off with the least significant byte and go up from there. So that would be A8 is the first byte. That's the least significant one. After that is CE. After that is those two Fs. And, oh, it still says invalid address 0x73.2F2F6E. So let's see, one really annoying thing about binary exploitation is debugging. So let's see what that really is. Let's see, what was that? IR. We're looking at 73.6E. So where does this start? 73, this is where it starts. And Interesting. Let's see here. We have 100, and then we had 22. We're at 132 here. So for some reason, this binary is looking at this part of the shellcode. So what I'm going to do is sometimes shellcodes don't work. So what I'm going to do is use a different shellcode. This is the bin bash shellcode. It's 33 bytes long. And the reason why some shellcodes don't work is still beyond me. There's certain videos that you could watch about like why certain shellcodes work sometimes and other times they don't, but I still do not quite understand. So 89, okay, let me just make sure really quick. 89 plus 33 plus 10 is 132. Okay, that's what we want. And let's see here. EIP now points to a different part in the shellcode. So this might be something strange with my particular machine. I think I might even have ASLR on. I'm not sure. So what I'm going to do is this program was taken from Narnia, which is a certain challenge in, it's called Over the Wire. I recommend looking at it, but let's go to their, Narnia 2. Narnia.labs.overthewire. There we go. Do I have the password? Oh. I might have an extra white space after that. This Narnia 2, it might be, it might not be Narnia. Let me check here. Narnia 2, Narnia 2 Over the Wire. Where's Over the Wire? Narnia.labs.over. Oh, 226. That's the problem. Okay. So let's do this again. Now here on Narnia 2. Okay, so we'll start let's go where we stopped. So that would be here. Print the 90 shellcodes. Then we got 110. Plus the shellcode here. Plus that would be, I'm gonna put another extra 90 times 10. So this is 132, so let's make this 100 like that. Okay, and now let's put B's and see what happens. So we were successfully controlled this. Let's look at ESP, the stack pointer. ESP stands for stack pointer. And here it is. So we want to be at D50C. Or we could choose FFD4FC. Let's try that. So FC D4 FF. And we received an illegal instruction. And that is when that happens, that means that when the program compiled, it saw some kind of assembly, and the assembly had some kind of instruction that was not clear to the computer. It was basically like traceback, like from going back from Python, some kind of syntax error basically. So we can just change that by slightly modifying this value to a whole bunch of different tries. We can try legal instruction. Oh, I forgot to look. D530, it's looking at, so what it happens is it goes past this code right here. And the shell code executes somewhere, like it doesn't execute exactly how it was supposed to. So I'm going to go back to the bash shellcode and copy this, which is 11 bytes more than the previous one. So this would be 89 then. And let's go here. Okay, it's at the B's, so let's go again here. All right, so let's try E8, D4 E8. Again, it has some kind of, it goes back. This happens so many times, like you just gotta brute force these addresses, and it doesn't look like we have enough time. Basically, you would have to keep on brute forcing these kind of addresses. This happens sometimes, and eventually you end up getting it. Not sure why it's not working now, because I tried this last night and it did work. But anyways, that's binary exploitation for you. It can be like this. Quit anyway, yes. So that was a buffer overflow example. Now let's go to the next example, which is printf. And so when I was competing in a certain competition, we had this kind of challenge. When I was competing in the capture the flag tournament, we had a challenge to connect to a server and make it leak memory. And this was done using the printf function, which is not considered a vulnerable function because it really isn't vulnerable. But if you put user input directly into the function as an argument, then you are making your program insecure. And this is because you can put format strings into the function. Stuff like %p or %x or %n, which is a whole, I would like to get into that, but we don't have enough time. So I'm just going to be talking about the %p for this presentation. And for this program we see right here, please.c, we have a buffer of 200 hex bytes and a flag. And so basically this just opens the flag, see if the file exists. If it doesn't, then just prints out an error message. Otherwise, it asks you, what do you say? And you put in some kind of string, and it compares the string to the word please. And if please is present within the string, then it will do this vulnerable printf buffer. So what we can do is pass %p directly into this printf and potentially leak the contents of flag.txt. And the reason we're able to leak the contents of flag.txt is because it's loaded into the binary in this line right here. So when it's loaded into the binary, that means it's in the memory of the program. So when we run this function, it says, what do you say? I don't know. And it just exit. What if we say please? Then what happens? It just says please to you too. What if we write please %p, which stands for pointer? Then it says please, and it leaks out memory. So what we can do potentially is leak memory from the binary. So what if we do something like print please followed by %p. Let's do 100 of these. Let's see what happens. and pipe it over to the program. And what we see is a whole bunch of addresses, a bunch of patterns that looks like 7025, 7025. And what that is just hex for percent and P. P is the 70, I believe, and percent is 25 in hex. So after printing all of this, it does nil, 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 and then it prints out this part, 0x336, all of this weird address stuff. And the reason that this is important is if you look really closely, let me print a little more. If you look closely, this kind of resembles like just regular ASCII kind of letters. You have 55, 98, 96. These are all just regular kind of ASCII letters. So if we were to put this into hex, converting this hex into ASCII, we'll see quite an interesting discovery. So here, I'll first let's notice where should I start? Right, let's start. Yeah, here's where the ASCII characters start. So let's copy this. Let's put this into the hex to ASCII converter. And we just put this. It's a little ugly. We gotta kind of separate it like this.
You got 10 minutes.
Oh, 10 minutes. Okay.
Actually, no, sorry. It's
How long?
5.
5 minutes? Oh, okay. So I'll go over this really quickly. So what we see here is really strange. We see caution. It looks very weird because this is a little endian binary. So it goes from the smallest byte to the biggest. That's why it's kind of reversed here. But although it's kind of jumbled up, if you spend enough time, you'll see that you can kind of decode this and make it looks like I'm actually missing a couple of letters. I think maybe right here, 30, 78, 39. Let's try this. We see this. This is the full string, and when I was doing this competition, I saw this full string and I was trying to make sense of it. How am I going to get the flag from this weird looking string? Well, you just kind of have to sit on it for a while, and eventually what you get is flag.txt. Flag, please printf with caution. And you could see that kind of what it says right here. Kind of. I mean, you got the flag here, printf. You have to rearrange it. So this might seem like kind of a weird thing. When are you ever going to be leaking memory addresses or contents from a binary or any kind of program for that matter? When would that even be useful? Well, Heartbleed is an example. Heartbleed was not a printf vulnerability. It was a problem with OpenSSL. I won't go into the full details of the vulnerability. We're kind of low on time. But basically what happened is memory was leaked from servers that contained credit cards and credentials, and hackers from all over the world, they gained all this sensitive information. And unfortunately with security, a lot of companies still have not patched this vulnerability, even though an update is out. And as was common, with buffer overflow as well, this was due to a lack of boundary checks. What happened is an attacker would say, the message basically asks you, hey, are you sending a message? And the attacker says, yeah, I'm sending you a message that's 1,000, or it's 1 kilobyte long. But the attacker would lie. He wouldn't send a message that's like 1 kilobyte long. He would send a message that's like 10 bytes long. So the server receives a message that's 10 bytes long. He expects a 1 kilobyte message. So the server is like, well, what do I even do with this? So the server kind of freaks out, and it ends up just throwing up all of its memory. And what happens is the attacker, he gets all of this memory just leaking all over to his system. And so it was discovered that 64 kilobytes at a time could be leaked from the vulnerable server. But you could just do it an infinite amount of times. You could leak all the memory. But anyways, that was this presentation about binary exploitation. And hope you learned something about printf, about buffer overflows. This is Heartbleed is a buffer overread because you read more than you gave, and it's from a lack of boundary checks. And yeah, that's the end of this presentation. Thanks for coming.